Today's lesson, section 6.4, exponential growth and decay. Let's take a look at a couple pictures here. So a reminder, we've talked before about linear growth, which would be equations of lines. So as you look at this graph, you can see that if I put a point right in the middle of these bars and connected a line, it seems like whatever this is dealing with, the situation is growing in a linear fashion where we see a consistent rise over run, which is slope. Exponential growth is not the same thing. So in exponential growth, what you see is a curve that starts off growing slowly, and then as time moves on, grows faster and faster and faster. And that is growing by a process of multiplication. That's the difference between the two. Let's go down here and take a look at the formula for exponential growth. I want everybody to study that, and then we're going to move on to some questions. How about that first question? How can you write 75% in decimal form? Well, 75%, a percent is equal to a number out of 100. So if that's the case in this situation, 75% means 75 over 100, which means it's the number 0.75, isn't it? So how could I write 115% in decimal form? Well, that would be 115 over 100 out of 100, which would be 1.15. Keep that in mind. Look at the difference between those two decimals. One is growth, one is decay. The 0.75 is less than 1. That would represent something getting smaller over time if you keep multiplying by 0.75. The 1.15 would represent something growing 15% more every instant. So let's go ahead and take a look at a couple questions, see if we can answer some of these. All right, so the inaugural attendance of an annual music festival is 150,000. The attendance Y increases by 8% each year. Write two forms of an exponential growth function that represents the attendance after 2 years. All right, I'm gonna go ahead and get us started on this. So Y represents the attendance. I'll highlight a couple things here for you. That's the first part. Okay. Now, how many people do we have originally? We have 150,000, right? So your initial value always goes in that spot. That's the inaugural attendance, which means it's the beginning amount. So the beginning amount always goes right there in your exponential equation. And then you need to represent the growth factor next. So when we represent the growth factor, there should be a percentage associated with this. So it's increasing by 8% each year. So if it's increasing, then this number needs to be over 100. It needs to be 108%. So here's the deal. We can't write this. When you calculate with percentages, you cannot write the percentage form. You need to write the decimal form of this. So there's two ways we could do it. One way we could do it is say 1 is the same as 100% plus 0.08, which represents 8%. And then the last thing we have to talk about is that this is going to be happening year after year after year after year. So we need an exponent, which allows for repeated multiplication over and over and over again. So that's one form of this. Now, the other form that would work would be almost identical. in appearance. And it is identical with respect to the way you calculate it. So what I'm going to do is I'm going to take that same number and just add them together. It's the same thing. So the next question then is, well, how many people will attend the festival in the 5th year? Well, that means that I will just merely replace the exponent with a 5. It's after 5 versions of repeated multiplication. And it says to round it, so I'll use a couple little squiggly lines to represent that. So let's do this. You need to know how to use your calculator. There's 150,000, parentheses. Now you could use 1 plus 0.08, that's fine. You need to use the exponent key. It says to round it to the nearest 1,000. So for me, that'd be the third number. Okay, and the number next to it's a 5, which is big enough to round it up. I'm sorry, wait a minute. It doesn't say thousandth. It says to the nearest 1,000. So thousands is this number right here, okay? So what I'm going to do is look at the next number, and it's not big enough to round that up. So we're going to just say it's 220,000. Now, if you didn't round it, it's no big deal. That's fine. But that's the way that would work. All right, let's go on to the next problem. Let's see if we can do this again. Let's read this. The website has 500,000 members in 2010. The number of Y members increases by 15% each year. Right? 2 forms of this situation. Okay, here we go. Okay, what's my initial amount? I'm starting with 500,000 people. That's going to go right here. Next thing, what's my growth factor? Let's see if we can identify that. Increases by 15%. So that means it's going to be 100% plus 15%. Okay? For an unknown amount of years after 2010. I'm going to circle this. You see this? It's after 2010. That's important. Okay, now the other version of this formula will look identical to it except for the growth factor. We'll just merely add the numbers together, but they're both the same equation. How many members will there be in 2016? This is very important. See if you can figure that out. Well, the key to that is knowing that the exponent represents the year after 2010. So 2016 minus 2010 is 6 years. That's crucial to getting this problem done correctly. So my equation, you can use either form you want, needs to be raised to the 6th power. We're going to round to the nearest 10,000, I guess, in this case, but that's fine if you don't round, to tell you the truth, but it is a good idea to learn how to round. So it's 500,000. Okay, make sure you type in these numbers correctly. 1.15 raised to the 6th power. Okay, so the 10,000 is this 5 right here. The 6 next to it is big enough to raise up, so it'll be 116,000. All righty, let's go on. There's another one. Let's see if we can get this done. Everybody study that and see if you can write it out. All right. The initial purchase, $20,000. See if we can get our growth factor here. Now, I don't know if you know what this means, but if it depreciates, that means it goes down. So here's how I'm going to write this. 1 100 minus 12.5% as a decimal looks like this. That's a pretty tough one to work with, but that's the way it's going to look per year. Okay, everybody? Now, what's the other form of this? Let's take a look. So it's $20,000. And then what I need to do is maybe go to my calculator. Let's see, what is 1 minus 0.125? Well, that's 0.875. That's what I could put in here, which means 87.5% of this car remains, a value remains every year. So how much is it worth after 5 years? Well, that will be the exponent that we use. Let's see if we can calculate that. So that would be a $20,000 car depreciating and leaving itself only 87.5% for 5 years. It doesn't say what we should round to, but it's money. So we should always round to the hundredth or the whole dollar, whatever you want to do on this is no big deal. 0.875 rounded to 5 years later. Okay. I'd say about $10,258 would be okay. And if you want to take that out to the hundredth, go ahead, but you get the idea. All right, let's move along.